On number 1, we want to evaluate the given expression when t equals 18. So simply plug in 18 for t and then type it into a calculator. So 30 times 1.45 raised up to 18 divided by 2, which would be a 9. And then just type it in. And I didn't give you rounding directions. Let's round to the nearest hundredth, since we often round to 2 decimal places. So in the calculator, it gives me 850.028. Since this 8 is greater than 5, we want to round this up to 850.03. On number 2, 5, negative 3, and negative 2, 1 are on f of x. What points would be on f inverse x? You simply switch your x and y coordinates to get points on an inverse. So just switch x and y for both of those points given. That's all they want you to do. On number 3, everything's already on one side equal to 0. So we want to set each factor equal to 0 and solve for x. That first factor, 2x plus 3, that's already factored as much as it can be factored. But that second factor, x squared minus 16, that's a difference of 2 squares. So we can actually factor that a little bit more. So a difference of 2 squares, you do the square root of the first term, and you put that in the first slot of your 2 sets of parentheses. So the square root of x squared is x. So I put an x and an x in the first slot of parentheses. The second term is the 16. Square root of 16 is 4. So I put 4 in the back slot of each set of parentheses. Make one positive and one negative. At this point, we set each factor equal to 0 and solve for x. Because the only way I can multiply factors together and get an answer of 0 is if at least one of those factors is 0. And we don't know which one's going to be 0, but we know at least one of them is going to be 0. So we have to set all of the factors equal to 0 and solve for x. So negative 3 halves. Let me make that 3 look a little bit more like a 3. Negative 3 halves is one answer. Negative 4 is a second answer. And then positive 4 is a third answer. That's it. That's all they're looking for on that one. On number 4, we want to find the point of intersection of those two equations. So if we were to graph these lines, we want to say the xy coordinates where the lines intersect. This is just a system of equations. Since both equations are not solved for a single variable, it would probably be easiest to do elimination. When you set up your problem for elimination, you want to make sure that you stack your x's on top of each other, stack your y's on top of each other, and then stack your constants on top of each other so that everything is lined up nicely. Then, pick a variable to eliminate. On this particular problem, it doesn't really matter which one you pick. They're both the same level of difficulty in order to eliminate one of the variables. I'm going to go with the x's. So when I look at the x's, I'm looking at the coefficients, negative 3 and 2. I want to use the least common multiple of 2 and 3. And I want to make those x's have opposite coefficients. So to get the least common multiple of 2 and 3, I would maybe list out multiples of 2 and 3, and then just find the number that's smallest that they have in common. Multiples of 2 are counting by 2. So 2, 4, 6, 8, etc. Multiples of 3 are counting by 3. 3, 6, 9, etc. So the smallest multiple they have in common is 6. So let me make the x's 6 and negative 6. Since that top equation, so I'm looking right here, since that top equation already has a negative and the bottom equation already has a positive, they're already going to be opposites of each other. So that's convenient for us. Looking at the top equation, I want to turn that into negative 6x. So I'm thinking to myself, what number do I need to multiply by to make that top equation negative 6x? So 2. 2 times negative 3 is going to turn into negative 6x. Looking at the bottom equation, I'm thinking to myself, what number do I need to multiply by to make that a 6x? So 3. 3 times 2 will turn the bottom into 6x. At this point, I need to make sure that I distribute the numbers in front to all the terms in the equation behind it, even past the equal sign. So for that first equation, I get 2 times negative 3x is negative 6x. 2 times negative 3y is negative 6y. 2 times 3 is 6. Do the same thing for the bottom equation. 3 times 2x is 6x. 3 times 2y is 6y. 3 times negative 2 is negative 6. At this point, we want to add down the columns. So negative 6x plus 6x cancels out. Negative 6y plus 6y also cancels out. And then 6 plus negative 6 also cancels out. This is kind of a unique situation. Does 0 equal 0? Is that a true statement? Yes. So all this is saying is that our two original equations are actually equations of the exact same line. So there's infinitely many solutions. Because again, those two equations are equations of the same line. If we had a similar problem, but we got down to the end and we got something like 15 equals 0, since 15 doesn't equal 0, that would be a no solutions problem because the two lines that they gave us were parallel, so they didn't intersect at all. But for this one, since 0 equals 0 is a true statement, we have infinitely many solutions. Those two lines are actually the same line. Looking at number 5, we want to algebraically determine the inverse of the function. So before we get too far, we want to rewrite f of x as y. Remember, it's just a different notation. We're switching from function notation to just letting f of x equal y. It's kind of like a step 0. Then switch your x and your y. And then now that we've done that, we're going to solve for y by doing order of operations backwards. So I'm going to subtract 2 from both sides. And remember, on the left side of the equation, x and negative 2 are not like terms. So I'm not going to try to combine those. I'm just going to leave it x minus 2. Then I'm going to get rid of that negative 6. I'm going to undo multiplication by doing division. And then that would be it. X minus 2 all over negative 6 equals y. If we know our answer is still a function, we can use that inverse notation. So I happen to know that the answer we got is still a function. So I could do f inverse x and then equals x minus 2 over negative 6. And I know that new equation is a function because that's actually just a line. And lines are functions because they pass the vertical line test. On number 6, use the table to determine what the price will be at 4 years. Don't overthink it. I know it seems way too easy. We literally just want you to be able to read a table. So that's all we want you to do is just say, okay, go down to 4 years, there's the price, done. Number 7, describe the transformations on each parent function f of x to create a new function g of x. So we're just talking about transformation notation that we've done a million times over. We've transformed quadratics, cubics, quartic, radical functions, absolute value functions back in Math 2. So that number on the outside, so in this case the 2, that's going to be a vertical stretch because it is larger than 1. That minus 3 is inside the parentheses. So anything inside the parentheses has to do with a horizontal transformation. So that's going to be a horizontal translation. And remember, the horizontal ones are always the opposite of what we think they should be. So that's going to be to the right 3. The plus 1 in the back, that's a vertical translation, and those are as they should be. So up is positive, down is negative. Vertical translation up 1. For part B, the x plus 1, think of that as being done directly to the x. So if we were doing this in a different notation, that would be inside the parentheses. So the plus 1 is going to be a horizontal translation left 1. The minus 8 in the back should be a vertical translation down 8 because it's not done directly to the x. It would be outside the parentheses if it was in that other notation. So vertical translation down 8. On number 8, looks like we have another system of equations. That first equation is already solved for a single variable, so it would be much easier to do substitution instead of elimination on this problem. So we know that y is equal to 2x plus 1, so we're just going to take 2x plus 1, we're going to substitute it in for y in parentheses in that second equation. So again, this 2x plus 1 is getting substituted in for y. And then from here, we should be able to just solve like normal. So I'm going to distribute to get rid of the parentheses. I'm going to combine like terms. Minus 2, x equals 0. At this point, plug in 0 for x in technically either of the equations, but might as well make it easy on ourselves. Let's plug it in right here. It'll be much faster. So y equals 2 times 0 plus 1. So y equals 1. And then we've always been in the habit of writing our final answer as an ordered pair, x comma y, so 0 comma 1. What this means is if we were to graph those two equations, they would intersect at the point 0 comma 1. Number 9, what is the equation of the inverse of h of x equals the fifth root of x minus 4 plus 1? So this is like that previous problem where we're just doing an inverse algebraically. So we want to let h of x be y, and then we're going to switch our x and our y. And then we want to solve for y by doing order of operations backwards. So I want to isolate that radical first. So in order to isolate the radical, I have to subtract 1 from both sides. Now that the radical is all isolated, it's all by itself on one side of the equation, in order to undo a fifth root, I have to raise it up to the fifth power. Whatever I do to one side of the equation, I have to do to the other side of the equation to keep it balanced. I do not want you to multiply out x minus 1 to the fifth. I don't want you to multiply that out. So you could just leave it like I have it. And then raising a fifth root up to the fifth cancels out, and you're just left with what was underneath the radical, so y minus 4. And then we just keep solving like normal. So plus 4, plus 4. So then we get x minus 1 raised to the fifth plus 4 equals y. And that's it.